Hello everyone! This is the third part of the story about the possible impact of a giant asteroid in the recent past. And we're finally going to tell you how it happened. But first, a few clarifications. Firstly, for those who have not watched the first two parts, I recommend watching them first, so it will be easier to understand what I'm talking about. Secondly, all calculations, conclusions, and formulations were carried out by me personally. The rationale for each calculation is given and demonstrated in this film and previous parts. And now, let's get down to the most interesting, to the answers. So, how can you not notice the impact of a gigantic asteroid? And it's all about celestial mechanics. The fact is that there are no direct routes in space. Absolutely all objects are moving. And this is not just a chaotic movement, just where, but a clear route along a specific orbit. And this orbit is always around a certain center of mass. In our solar system, this center of mass is the Sun. And in order to fly from one planet to another, you need to perform a number of very complex maneuvers, each of which will be a transition from one orbit to another. That is, it will not be a straight line, but a very, very curved one. And the behavior of objects when approaching will be very different depending on their masses, sizes, and speeds. For example, if a pebble flies 10 to 20 meters in size, or even 100 meters in diameter, at a speed of, say, 25 to 30 kilometers per second, and even in parallel courses, then the Earth will immediately put it on its shoulder blades and drop it on itself practically without any resistance. If the speed of even such a small pebble is 35 to 40 kilometers per second, then the Earth will have to try hard. The meteorite's orbit will definitely change under the influence of gravity, but there will be no collision. It will simply fly past without giving the forces of gravity enough time to capture. If the pebble is more massive, like our 200-kilometer friend, then the collision process will depend on a huge number of factors, and in any case turn into an exciting dance of two celestial bodies around a common center of mass. Let's analyze this dance in more detail and find out why our initial size calculations were only approximate and were not of decisive importance. Here, it is worth immediately explaining some of the concepts used in the following. Perfectly round orbits practically do not exist. They are all elongated in one way or another. Some are elongated quite a bit and are practically indistinguishable from a circle. Other orbits are elongated like an egg. The point of the orbit that is located closest to the center of mass is called the perigee, pericenter, or perihelion, depending on the context. And the farthest part of the orbit is called apogee, epicenter, or apogelium, respectively. Now, it is necessary to understand by what rules celestial bodies generally move in our solar system. The first rule is that all bodies move in the same direction, around the common center of mass, the Sun. If you look at the plane of the ecliptical from the North Pole, it will be a counterclockwise direction. And if from the south, then vice versa, clockwise. That is, the movement in the opposite direction is almost impossible. The second rule is not so strict, but still also quite important. Objects must move plus or minus in one plane, which is called the plane of the ecliptic. Of course, each planet, comet, or asteroid has a certain inclination of its orbit to the general plane, but we will talk about this in other series. The third rule is that each object moves not just clockwise, but also necessarily has a center of mass around which it rotates. It's either a planet or a sun. In rare cases, this center is the center of our galaxy, but this applies only to those objects that have third and fourth cosmic velocities and appear in our system in transit, temporarily. Another important rule is speed. Each object has the first, second, or third cosmic velocity. and depending on it, it is either a satellite or a falling body or passing by. It is the speed, orbit, and mass that are determining quantities on which further relationships between objects depend. Now we can proceed to further investigation. Let's figure out what orbits and trajectories our asteroid could crash into the Earth. Number 1. Oncoming trajectory. This trajectory assumes a frontal collision with the ground at an angle of 90 degrees. It is this trajectory that is the most catastrophic and destructive. In this case, the speed of the collision will consist of the speed of the Earth's movement around the Sun, about 30 kilometers per second, plus the speed of the asteroid, about 40 kilometers per second. That is 70 kilometers per second and more. Such collisions, as can be seen in the diagram, occur in the morning. Interesting detail, right? How does this option relate to the rules of the solar system? Badly. Now, of course, there are such morning collisions, but they are all directed at an acute angle to the ground. There are practically no frontal ones. Precisely because for a frontal collision, our meteorite must move around the Sun against the general direction of movement of the planets. Of course, this is possible, but this probability is approaching absolute zero. In addition, if this scenario had happened, then perhaps the Earth would no longer exist, but instead there was another asteroid belt. Number 2. The second option is more common. It is a catching up trajectory. In this case, the meteorite will move according to all the rules of motion of the solar system, and since its speed is higher, it will catch up with the Earth and the collision speed will be 10 to 15 kilometers per second. Such collisions are most likely. If the collision is direct at an angle of 90 degrees, then it occurs in the evening, at sunset, but in the vast majority of cases the approach occurs at an acute angle, either closer to midnight, a living example is meteor showers, or during the day. The direction of movement of such meteorites is from east to west if during the day, or from west to east if at night. Of course, there are options depending on the angle of inclination of the asteroid's orbit to the Earth's orbit. How does this option fit in with our suspect? Perfectly consistent, high probability, but there are a few nuances. The fact is that if the pericenter of the orbit of such an object is located between the Earth and the Sun, then this object will fly past the Earth at its maximum speed, about 45 kilometers per second, and the Earth simply will not have enough time to attract it to itself. In addition, the closer the asteroid's orbit pericenter is to the Sun, the steeper the turn it makes near the Sun, and the greater the gravitational effect it has on him. In other words, only very small and fast objects move in such orbits, and all large ones are simply torn apart by the gravitational forces of the Sun. Therefore, we are interested in asteroids that have the extreme point of their orbit, the pericenter, somewhere in the region of Venus, Earth, or even Mars. The largest asteroids fly along such transit trajectories. Consider this option as the most appropriate and likely. Let's call it transit. Number 3. Transit option. In this case, our planet is in the path of an asteroid or comet going along the route the Sun, Jupiter or the Sun, Saturn, or even the trans-Uranium route. In this case, the impact on the planet will also have to be from the side, either at sunset or at dawn, depending on which part of its route the object will be located, but definitely not during the day and not at night. Collision speeds will be either 30 kilometers per second if in the morning, or the object will touch the atmosphere or even the surface and fly further if in the evening. There are also nuances related, again, to the angle of inclination of the asteroid's orbit, as well as the location of its perihelion point. This transit option is the most possible of all. Here, you have a huge number of asteroids and comets that are still active, and a huge selection of asteroids for every taste, size, mass, and density. That is, if such a huge 200-kilometer-long body flew to us, then with a huge probability of everything exactly along this trajectory. We continue the analysis. Let's answer the question, is a direct collision possible? Of course, yes, but the probability of hitting one microscopic point on the scale of the solar system into another of the same is almost zero. There is a much greater probability of an asteroid hitting the Earth's gravitational field and a gradual deviation of the orbit to the side. This probability is almost 100%. And again, possible scenarios are possible. In one case, a gradual deviation of the asteroid's orbit will cause it to fall into the Sun. In the other, it will make a gravitational maneuver around the Sun and, having gained the fourth cosmic velocity, will fly out of the solar system altogether. In some variants, he will even collide with Venus, Mercury. But these are all the consequences of the short-term influence of the Earth's gravity on the asteroid. In all these options, the asteroid will only deviate from its route, but will not slow down. But we are interested in another option, in which the asteroid will be under the influence of the gravitational field of the Earth for a long time, and will be able to slow down to the second cosmic velocity. To do this, the object must be as long as possible between the Earth and the Sun on the way to the Sun, or between the Earth and Mars on the way from the Sun. It is probably best if the first contact occurs precisely on the way from the Sun and at a sufficiently large distance from Earth. In this case, the Earth will simultaneously deflect the asteroid's orbit and slow it down. The mass of the object also plays a big role here. If the object is too massive, then effective braking will not work. If the object is small, it will immediately fall to the ground like an ordinary meteorite. In other words, the class of asteroids with a diameter from 100 to 1,000 kilometers, calculated and found by us in that last part, fits perfectly. The hypothesis is confirmed by the work of the Massachusetts Institute of Technology group led by Richard Binzel, who, based on their observations, compiled a computer model that tracked the movements of asteroids and the Earth over the past 500,000 years. It turned out that during this time a huge number of asteroids approached the Earth at a distance of less than 100,000 kilometers, that is, 3.5 times closer to the Moon. And on each of them there were traces of the gravitational influence of the Earth. So what will happen to the asteroid if its speed relative to the Earth decreases to the second space velocity? To be precise, up to 11 kilometers per second, or even less. Then the object will return to the ground, become his companion. But more on that later. First, let's find out the mechanism and trajectoria on which this is possible. The ideal option would be such a coincidence in which the asteroid would catch up with the Earth, moving from the periapsis of its orbit to the apocenter, and at the same time would be on the night side of the Earth. Such a periapsis point would not be near the Sun as usual, but between the orbits of the Earth and Mars. There is nothing contrary to the rules in such an orbit, but it is not only possible, but also indirectly confirms the assumption about the size of the object, since such orbits are characteristic, firstly, of massive bodies, and secondly, of asteroids in transuranic orbits. A living example is the asteroid 2060 Charon, which has a diameter of 160 kilometers. So, our asteroid is moving at a speed of about 30 to 40 kilometers per second, moving away from its periapsis towards the apocenter, that is, deep into space, and at this moment it catches up with the Earth, which is moving in a parallel course at a speed of 30 kilometers per second. Thus, their relative speed to each other is no more than 15 kilometers per second. That is, the Earth needs to slow down. This object is only a couple of kilometers per second. Of course, this is also a huge speed, but since the objects are moving in parallel courses for some time, the Earth's gravitational field has more than enough time to slow down. Let's figure out how much it is. As a basis, we again take obvious objects, for example, the Moon, which is exactly in the gravitational field of the Earth and does not leave us anywhere. The distance to it is 380,000 kilometers, which means that the gravity well along which our asteroid flew occupied 380 times 2 equals 760,000 kilometers. With a relative speed of 15 kilometers per second, the asteroid will cover this path in 14 hours. And at the most probable speed of 12 kilometers per second, then 18 hours at all. And all this time it will be slowed down by the gravitational field of the Earth. It is worth noting once again that the speed of an asteroid is an average value, since at different points in their orbit they move at different speeds. Being at the far point of the orbit, deep in space behind Jupiter, their speed is from 7 to 20 kilometers per second. And at the point closest to the Sun, it accelerates to 50 to 60 kilometers per second. Thus, the speed of 40 kilometers per second chosen by us as a sample is the maximum speed of an asteroid at this distance from the Sun. The average speed of asteroids near the Earth is 40 to 42 kilometers per second. At a higher speed, it will simply fly away from the system. In other words, as soon as the asteroid on the route we have built has entered the gravitational field of the Earth, it will become very difficult to go back. But this does not mean that he will immediately fall and we will all die. No, the most interesting part is just beginning. Under the influence of the Earth's gravity, the asteroid will not only slow down, its orbit will begin to smoothly bend in the opposite direction, and at a certain stage, it will turn back and occupy the Earth's orbit. The distance at which it will turn around again depends heavily on its size, mass, and initial speed. The higher the initial mass and velocity, the farther away will be the turning point, the epicenter of the new orbit, and the more elongated it will be. From this moment, a common center of mass is formed between the Earth and the asteroid, around which they begin to rotate mutually. The speed of the asteroid does not allow it to escape beyond the gravitational field of the Earth, but it is still quite sufficient for rotation in a given orbit. There is no need to look far for an example. It is always in front of us. It is the Moon. But the Moon is still a separate conversation. Its orbit is almost round, but for our asteroid everything is not so. Its orbit is very elongated. However, now our asteroid has become a satellite of the Earth. Until the forces of gravity reduce its orbit to a dangerous level. How long can this go on? Let's guess. One revolution of the Moon around the Earth takes about 27 days. This means that our asteroid's turnover took at least no less. But the speed of rotation of the Moon in its orbit is about 1 kilometer per second, and our asteroid is still 10 times faster. Not for long, of course, but at first he made a revolution around the Earth in about 82 hours. That is about 3.5 days. And this means that the final dance of the asteroid around the Earth could take months, years, and even decades. But at the points of pericenter and apicenter, which are at a considerable distance from the Earth, perhaps even beyond the orbit of the Moon, strong gravitational tides begin to act. This is when inertia pulls you in one direction and gravity in the other. And if the object is large, these forces begin to tear the object into smaller pieces. Such processes are constantly observed in the nearest space. The closest example is the asteroid belt. We will consider the rest of the examples a little later, but for now let's remember two things. The object temporarily, for several years, took a more or less stable orbit. It is torn into several parts, its orbit is elongated, and in some places passes quite close to the Earth. Let me explain for those who have not watched the previous parts. In any case, tidal gravitational forces will act on any object, but how quickly they tear it apart depends on the composition and density of the object. An iron meteorite, for example, is almost impossible to break until it reaches a certain size. But our object consists almost entirely of compacted dense sand and clay, explained in the previous parts. Therefore, our object will be torn into several large parts immediately or almost immediately. What will the observer from the ground see in this case? Nothing special, just 2 or 3 new moons appeared in the sky. If an asteroid with a diameter of 200 kilometers passes by the Earth at a distance of 22,500 kilometers, it will appear to be just the size of the moon. With only one difference, it will never be visible as a full moon. It will always be visible only as a crescent. Because at this distance, being in the shadow of the Earth, it will never be fully illuminated. Here's a month for you. And it was precisely these fragments of a torn asteroid that may have been the missing moons. What will happen to our object? Our objects already now, next. And then 2 things will happen at once. First, the force of gravity will gradually reduce their orbit closer and closer to the Earth. At the same time, gravitational forces will continue to chip off more and more pieces and shred them into smaller and smaller components. Gradually, over time, all the lightest and least dense parts will be torn down to a state of dust and occupy a lower orbit, thus forming a so-called accretion disk around the Earth. Or in common parlance, rings. Exactly the same rings we see now in Saturn. The same rings are in uranium and even Jupiter and Neptune. What can I say? Even Chiron, which is only 166 kilometers in diameter, also has such rings, but small. The brightest and most famous, of course, are those of Saturn. Such rings can circle around the planet, gradually descending and falling to the surface for many years. At Saturn, they consist mainly of ice crystals, which has a density of 1, so they will not disappear soon. However, our rings are made of sand and clay, which is twice as heavy, so they fall to the surface much more efficiently, while simultaneously mixing in the upper layers of the then even denser atmosphere with water and spreading over the entire surface. But even before that, the heaviest parts of our asteroid, apparently consisting of basalt and iron, having freed themselves from masses of sand and dust, greatly decreased in size, lost inertia and mass, and now can safely fall onto the planet. All of them will fall in different latitudes of the planet, but always on the same meridian and almost simultaneously. This is due to the fact that the original body, having split at the far end of the orbit under the influence of tidal forces, nevertheless reported to all 3 fragments the same acceleration and almost the same direction. The only difference is that they must fly apart from each other at a slight angle due to the split. And the farther from the Earth the split occurred, the greater the distance between them on the meridian of fall, right? But since all parts fell apart at the same time and acquired the same initial momentum, but in opposite directions, the distance between them should be approximately the same, right? So. And what about our rings, our accretion disk of sand and clay? And it will still fall to the ground for a long time, maybe even several years, at the same time blocking the sun and causing a cooling. In addition, since our object was heterogeneous, the denser fragments survived until the direct fall, while the lighter ones lined up in a ring along the equator in the plane of the ecliptic and fell to the ground for a long time. I think that everything has already become clear to many, and yet we must move on to the evidence. Many already know about the 3 marks on the surface of the Earth in the oceans. The first separates Antarctica and South America, forming the Drake Strait. The second, practically at the equator, also separates North and South America in the Caribbean Sea. The third at the North Pole, at the bottom of the Arctic Ocean. All 3 marks start at approximately the same 50th meridian. All 3 have very similar widths and depths that range from 450 kilometers central, 550 kilometers south, and 700 kilometers north. All 3 have approximately the same length of 1960, 2300, and 1910 kilometers, and the distance between them is completely the same, In all cases, it is 8,250 kilometers. What does this mean? A slight difference in the length and width of the track indicates slightly different sizes and different terrain at the collision site. And it is not surprising. The asteroid could not split into absolutely equal parts. But to give all parts absolutely the same momentum and speed, he not only could, but was obliged. Therefore, all 3 fragments fell to the ground at approximately the same meridian. And that is why there is absolutely the same distance between them. When they split, they flew out like shrapnel from a shotgun. But that's not all. Thanks to the mechanism already known to us for calculating the consequences of the fall of celestial bodies, we calculate that each of these 3 fragments had a diameter of 170, 200, and 250 kilometers. As they arrived almost simultaneously, with the only difference that the heaviest piece, the one that fell into the Arctic Ocean, arrived a little later, about 4 to 5 hours. Plus another 200-kilometer ball of clay and sand, which fell out of the accretion disk and atmosphere over a long period of time. And this is the same quartz dust, sand, and clay that has been distributed over the entire surface of the globe and deserts. That is, we get the final diameter of the asteroid, at least 400 kilometers. No less. But this is already quite accurate data. What else does it give us? Well, for example, knowing the distance between the points of incidence and the angle of entry, we can quite accurately determine the epicenter of its orbit at the time of the split. It is 472,714 kilometers. With the theoretical part, perhaps everything. And even the evidentiary part is there. The above is quite enough to say with absolute probability that there was such a scenario in the history of the planet once, for sure. But this is not the end. To be continued.